Composition of functions, introduction. So far we've been building our understanding of what functions are and how they behave, things like their domains, ranges, and different ways to represent them. Now, we're going to move on to something really powerful called the composition of functions. Think of it like building with Legos. We have individual bricks, those are our functions. Composition is like taking those bricks and combining them to create something entirely new, a more complex structure, which is our new function. Essentially, what composition lets us do is take two functions and combine them. We don't just add or subtract them, but we apply one function to the result of another. So, imagine you have a function that does something to a number, and then you take the output of that function and feed it into another function. That's composition in a nutshell. We'll be looking at how to write this mathematically and work through some examples in the coming slides, but this is the core idea we're starting with. Composition of functions, understanding the concept. So let's move on to understanding how composition actually works. On this slide, we're going to lay out the groundwork for combining functions. We're going to consider two functions. The first function, we'll call it f, takes elements from a set A and maps them or sends them to a set B. Think of f as a machine. You put something from set A into the machine, and it spits out something in set B. Now we have a second function, g, which takes elements from set B. Notice this is important and maps them to a set C. So, g also acts like a machine, but its input comes from set B, and its output goes to set C. Now here's a crucial point. Notice that the codomain of f, that's the set of all possible outputs of f, which is b, is exactly the domain of g, that's the set of all possible inputs of g, which is also b. This matching up is absolutely essential for us to be able to compose these functions. If they didn't match, we wouldn't be able to feed the output of f into g. When we do have this compatibility, we can create a new function by combining g and f. We call this composition and we write it as g circle f. The circle symbol, O, signifies composition, and we read it as g of f. This new function, g of f, takes elements directly from set A and maps them to set C, effectively skipping set B as an intermediate step. Formally, we write this as g of f of x equals g of f of x. This means that to find the output of the composed function when you input a value x, you first apply the function f to x, getting f of x. Then you take that result, f of x, and apply the function g to it, giving you g of f of x. So we're essentially nesting functions, one inside the other. In simpler terms, to find the output of this combined function at a specific input, x, we first use function f on x, and then we use function g on whatever f of x turned out to be. We'll see this in action with some examples on the next slides, but this slide establishes the fundamental idea of how function composition works. Composition of functions, step-by-step explanation. So let's break down how composition of functions actually works step by step. This slide illustrates the process really clearly. We begin with an input. Imagine you have a value, let's call it x. This x comes from the domain of our first function, f. Remember from the previous slides, the domain of f is set A, so x is just some element belonging to set A. Next, we apply the function f to this input x. This means we substitute x into the rule that defines f, and whatever we get out is called f of x. This result, f of x, is an element of the codomain of f, which is set B. But importantly, this f of x also becomes the input for our next function, g. Remember, we talked about how the codomain of f has to match the domain of g for composition to even be possible. Now we take that result, f of x, and we apply the function g to it. So we're evaluating g at f of x, which gives us g of f of x. This final result, g of f of x, is an element of the codomain of g, which we called set C. Finally, g of f of x is the output of our combined function, the composition of g and f, which we write as g composed with f, and we denote it as g circle f. So, g circle f of x is simply equal to g of f of x. Essentially, we're feeding the output of one function into the next. This slide is crucial because it shows the order of operations. We're not just randomly plugging things in, we're applying f first, then g. We'll see how important that order is in a later slide when we look at common mistakes. But for now, make sure you understand this step-by-step process. It's the foundation of function composition. Composition of functions, example. So far we've discussed what composition of functions is, combining two functions. Now, let's solidify our understanding with a concrete example. We're going to work with three sets. A, B, and C. Set A contains the elements 1, 2, and 3. Set B contains the elements 4, 5, and 6. And finally, set C contains the elements 7, 8, and 9. We'll define two functions. F and G. Function F maps elements from set A to set B, and function G maps elements from set B to set C. Let's define these functions explicitly. We say that f of 1 equals 4, f of 2 equals 5, and f of 3 equals 6. Similarly, g of 4 equals 7, g of 5 equals 8, and g of 6 equals 9. Now, remember from the previous slides, the composition of g and f, written as g composed with f, or g of f, creates a new function that takes an element from A and maps it directly to an element in C. Let's call this new function h. So, h is equal to g composed with f, and it maps from A to C. Let's find what h does to some inputs. First, let's find h of 1. This is equal to g composed with f of 1. Remember, this means we first apply f to 1 and then apply g to the result. So f of 1 is 4 as we defined earlier. Then, we evaluate g of 4, which is 7. Therefore, h of 1 equals 7. Let's do the same for h of 2. G composed with f of 2 means we first find f of 2, which is 5. Then, we find g of 5, which is 8. So, h of 2 equals 8. Finally, let's find h of 3. G composed with f of 3 means we first find f of 3, which is 6. Then, we find g of 6, which is 9. So, h of 3 equals 9. Therefore, we can fully define the composed function h of 1 is 7, h of 2 is 8, and h of 3 is 9. This shows how the composition of functions works in practice. We're essentially chaining these functions together to create a new transformation from one set to another. In the next slide, we'll see how this works when the functions are defined by equations rather than just a list of values. Composition of functions, another example with functions defined by equations. So let's move on to another example of function composition, this time using functions defined by equations. As you remember from the previous slides, the key to composition is ensuring the codomain of one function matches the domain of the next. Here, we're defining our sets $, $b$, and $c$. $. Is the set of all real numbers, denoted by r, that are greater than or equal to 0 and less than or equal to 2. So, A contains all real numbers between 0 and 2, inclusive. $b$ and $c$ are both simply the set of all real numbers. Now let's define our functions f$ and g$. F$ maps elements from set $1 to set $b$, and it's defined as fx equals x1. In other words, the function f$ takes a value x and adds 1 to it. G$ maps elements from set $b$ to set $c$, and it's defined as g x equals x$ squared. So the function g$ takes a value x and squares it. Now we want to find the composition of g$ and f$, which we denote as g$ composed with f$ or g\circ f$. This new function, which we'll call h$, will map elements from set A directly to set C$. Let's find the expression for hx$. Remember, hx$ is the same as g\circ f, x$, and that means g fx$. So we start with the inner function fx$, which we know is x plus $1. Then we substitute that entire expression into the function g$. Therefore, g fx$ becomes g x plus $1. Since g x$ is x$ squared, we replace x with x plus 1. Giving us x plus $1 squared. Expanding that, we get x$ squared plus 2 times x$ plus 1. So hx equals x plus $1 squared. Let's check this with a couple of examples. If $x is 0, then h $0 is $0 plus $1 squared, which equals 1 squared or simply 1. And if $x is 2, then h $2 is $2 plus $1 squared, which equals 3 squared or 9. This confirms that our composed function h, x, equals x plus $1 squared is working correctly. Remember, this is a crucial step. Verifying your result with specific values helps ensure you haven't made any algebraic errors. We'll build on this understanding in the next slides, so make sure you grasp this example thoroughly. Composition of functions, key takeaways. Let's recap what we've learned about composition of functions. This slide summarizes the key takeaways, and it's important you have these firmly in your mind before we move on to spotting common mistakes. First point, composition of functions combines two functions to create a new function. Think of it like building with Legos. You're taking two separate pieces and fitting them together to make something bigger and more complex. That, something bigger, is the new composed function. Next, and this is crucial, the codomain of the first function must be the domain of the second function. Remember from earlier slides, the codomain is the set of all possible output values of the first function, and the domain is the set of all possible input values of the second function. They need to connect. The output of the first function needs to be a valid input for the second. If they don't match up, the composition simply isn't defined. Now let's talk about notation. The composition is written as G circle F. The circle symbol, degrees, is how we denote composition. It's read as G of F. And importantly, it means we apply function f first, and then we apply function g. The order is absolutely vital, and we'll see why that's so important on the next slide when we discuss common errors. Finally, this just formalizes what we've been saying. The notation g\circ f, x $, which we read as g of f of x, is equal to g f x $. That means we take a value x, apply the function f to it, getting f of x, and then we apply the function g to that result. So we're plugging the output of f into g. Keep these 4 points in mind, and you'll be well equipped to tackle more complex composition problems. Now, let's move on to look at some typical mistakes students make, so you can avoid them. Composition of functions, common mistakes. First, and this is a big one, order matters. The composition of g of f, which we write as g circle f, is generally not the same as f of g. Remember, with function composition, we're applying functions one after the other. Think of it like putting on socks and shoes. You need to put the socks on before the shoes. Changing the order will give you a completely different result. So always be mindful of which function you're applying first. Next, let's talk about domain and codomain compatibility. We touched on this earlier when we introduced the concept, but it's worth repeating. Remember that for the composition to even be defined, the codomain, that's the set of all possible output values of the inner function, which is f in g of f, must match the domain, the set of all possible input values of the outer function, which is g. If these don't align, you simply can't compose the functions. It's like trying to fit a square peg into a round hole. It just won't work. Finally, confusing the notation. This is a simple but frequent error. Remember that when we write g of f of x, which is g circle f of x, it means we're applying f to x first and then applying g to the result of f of x. It does not mean we multiply g of x by f of x. It's g of f of x. The parentheses are important. Don't fall into the trap of thinking it's a simple multiplication of the two functions. Let's move on to the final slide, where we discuss some common mistakes students often make when dealing with the composition of functions. It's good to be aware of these before you get stuck on a problem, so pay close attention. So, keep these 3 points in mind as you practice composing functions, and you'll be well on your way to mastering this important concept. Are there any questions about these common mistakes before we wrap up?